Finally, we will discuss the full rotating atmospheric equation. So in the previous video on this, we discussed how once we add to Newton's law formulation of the equation, now we add that our body, our planet body is rotating, we get this equation. So we have the velocity on the left-hand side, or the change in velocity over time. And then we have the Coriolis force, we have the pressure gradient, we have the gravitational force with centrifugal force, and then we have friction. And in that video, what we did not take into account is that the Earth is a sphere. In the previous equation, we have the Earth as some sort of flat object or some sort of cube. And the Earth, however, is not a cube, it's spherical. So we need to include the effects of what's called curvature. So this will be the full equation set. So we have our equation in a rotating system, which we just discussed is this part of the equation. And we can break apart this term by using the product rule. So first what we do is, because we know that this term is ui plus vj plus wk, then we can take the derivative of each of those terms, and we'll have to do the product rule now. So we have du dt times I. So if you remember, dfg is equal to fdg plus gdf. So we did the derivative of the first one, du I, plus u di dt. And we do the same for j, same for k, and now we're good. So this part will be the left-hand side of our equation. And we need to deal with the right-hand side. Currently, it's still on the left-hand side, but we will subtract it to the other side. What we need to deal with is these terms. If we look here, we can look at this term. Here, this box is for this one, this box is for this one, and this box is for this one. When we break apart the total derivative of I, we get di dt, or partial I partial t, plus u partial I partial x, plus v partial j partial y, plus w partial k partial z. If you remember, df dt is equal to df dt partial I partial t plus u partial I partial x plus v partial j partial y plus w partial k partial z. So that's what we did here, here, and here. And I, the vector, is defined as, if we have x, y, and z, I is in this direction, j is in this direction, k is in this direction. The unit vectors never change in time. So that will always be 0. And you can show by looking geometrically which directions the I, j, and k vector are, and you'll find that j, sorry, this should be I. So I made a little mistake here. So this is I, this is I. Yeah, those are both I. So I does not change in the y or z direction either. It only changes in x. I is a function of x only. And for j, we also have it's not a function of z, but it is a function of y as well. So j is equal to a function of x and y. And same for z, or sorry, k, the z direction unit vector. K is a function of x and y. So I will show at the end of the video how we deal with the partial I partial x term. But for now, we know that partial I partial x is equal to, and let me correct this. This is not correct. This would be 1 over a cosine b. So we'll show that partial I partial x is equal to u times, actually, this part here. This u is this u. This v is this v. This w is this w is this w. And so we have u times partial I partial x will be 1 over a cosine phi in the r hat direction. And this u is this u. So if we take that out, and we know that r is negative sine phi j plus cosine phi k, we have u squared. And sorry, another mistake is in the negative r hat direction. So that's why there's a negative here, and then the a cosine phi on the bottom. And we know that tangent is sine over cos. So we have positive cancel out. So u squared sine over cosine tangent over a. And then the minus cosine over cosines cancel out. You get minus c squared over a. For this term, we have that partial j partial x is negative tangent phi over a, or tangent phi over a in the negative I direction. And partial j partial y is k hat over a, or 1 over a in the negative k hat direction. So we write it like negative tangent phi over ai minus k over a. And this v gets multiplied through, the u get multiplied through with this term. The v gets multiplied with this term. So we get u v negative tangent phi over ai, that's this. And then we get v times v, which is v squared, times negative k hat over a. So it's minus v squared over a k hat. Great. Now, finally, for the k direction, we have partial k partial x is I hat over a, and partial k partial y is negative j hat over a. Multiply the w out, the u goes here, the v goes here, and we'll get this will be uw. 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 So we'll get uw I hat over a minus vw j hat over a. That's this. Great. So now what we can do is we can take all the i's, which is this one and this one goes together, all the j's, this one and this one goes together, and this one and this one goes together. So again, we have du dt rotating is equal to these terms, which we can call du dt, which will be the left-hand side of our equation. And we have, additionally, we have these terms. So we'll keep calling this a, and a. Okay, back on track. So we have these terms, each of them is divided by a. So I just took that out and I grouped by I, j, and k, and you'll get terms that look like this. For I, we'll have uw minus uv tangent phi, which remember phi is latitude, if I forgot to mention. J, we have vw plus u squared tangent phi, and k, this full term is negative u squared plus v squared. Now, we also know from the previous video that the rotating momentum equation or atmospheric equation is in this form. So we now know that this is equal to this. So we can take these terms and subtract it on this side. And so doing that, we do show the part of the steps of the subtraction. Du dt vector is equal to pressure gradient plus friction plus gravity minus the Coriolis term, or is the Coriolis term, and then here are the curvature terms. So finally, we can, because this is in vector form, but this has been collapsed into its sort of, this is in unit vector form. These are in vector form. So there is no way currently known how to write these terms into a vector like we did in this case with omega vector cross u vector. And even in the past tried to figure it out. I also kind of gave up, and um, honestly, it's not necessary to really know that full version. It's just a neat way of writing things. So we can just write it in this form, where this is kind of the regular vector form, where anything like this, u v w, that would be equal to ui plus vj plus wk. Anything like this is I, this is j, this is k. So we can write it like that. So, for example, r hat is equal to x, y, z. Um, so to summarize, we have the total derivative, which is du vector dt is equal to the pressure gradient force plus the viscous force or friction force plus the gravity force, which also includes the centrifugal force inside of it. See, you have this term. When the k gets multiplied in, you only have this g in the z direction. And then this centrifugal force, this k and this k will be multiplied to be 1, and this centrifugal force will affect all dimensions, x, y, and z. And then we have a Coriolis force, and then what we just wrote right here, we have the 1 divided by r times the I, j, and k component. And I forgot to mention, we're going to let a equal to r. Before we use the letter a, because we didn't want to confuse with r or the r for rotating. But now we're going to use this r for the radius because there are no other like a's anywhere here. There's no a's. So we could use a, but I think I like r better. Because I personally mix up A with these alphas. So yeah. And in case you've forgotten, I've written down what the operators are. We have the gradient, which is this. We have the Laplacian of a vector, which is this. And we have, the Laplacian vector applies into multiple Laplacians. And each of those Laplacians is, for example, like this. And then we have the curl. So that takes care of everything. So as long as we know, a starting, we need to know u, v. I'll just write out the things we need to know to solve this equation. So to solve, we need u, v, and w, the velocities, and we need density, which is equal to 1 over alpha, and we need pressure. We need viscosity. So this is viscosity. And we already know gravity. And inside of the gravity term, you just have these omegas. So as long as we know the rotation speed of the Earth, we're good. So this is pretty constant, and we don't need to predict it. So that's fine. We know the radius of the Earth. We know the anywhere that we're doing this calculation, we know the latitude there. So latitude is fine. Yeah, and we have everything. So To solve this equation alone, you only need U, V, W, rho, pressure, and viscosity. So that's actually quite simple. Um, it could be much worse. And I do want to mention one thing or two things about the friction. This friction is for a incompressible fluid. And for air, air is compressible, right? So for the friction force, treating the friction as an incompressible friction is not is a pretty good approximation for air. So that's okay. But there is, you might find on the internet, a fuller version of this term, which I may discuss in the future if it's ever of interest to me or I learn more about it. Um, but for the most part, this term is um, usually actually left out of the equations, but I find it to be a very important term. So I'll probably look at that more in the future. Um, Also, you may be wondering, why the heck is the friction force positive? Because you'd be thinking, hey, you have more friction. So let's say friction goes up. Wouldn't velocity go down? And yes, you'd be right. So that's kind of the confusion that I had about this term. But it turns out this term is not really doing exactly what we think of when we think of friction. So the friction in the air, what this term is basically saying, when you're dealing with a Laplacian, that's a double derivative. That's basically equivalent to a double derivative. So, for example, this is the x version of that. It's a double derivative. And if you remember from calculus, if you have this shape, that's greater than zero. If you have this shape, that's less than zero. So you can think of if this term is greater than zero, you're dealing with, the change of velocity, how much velocity changes over space, and how much velocity change over space happens over space as well. So if this term is more and more gets more and more positive over time, um, sorry, this is negative. What that means is that greater than zero means that valleys, this is a valley, valleys are getting smaller. So the valley becomes more like this. And this being a mountain, this term here getting smaller and smaller, if it's less than zero, would mean that the mountain is flattening out. And so basically friction works to slow down this peaking of air. So that's important to know why it's positive if you ever forget. You may be wanting to put that it's positive. And I also want to mention now that gravity here is positive. Why do we do that? Well, it's simply because, well, we defined this term here. We decided to say that GM, gravity, is a negative. So we said that, um, well, actually, it's more intuitive to make it negative. So it all depends on our definition. I'm going to make it negative. And that means that we're defining GM as a positive number. And remember, GM is equal to gravitational constant times mass divided by radius squared, I think. Yeah, check that. Look at gravity. Yes, negative GM over R squared. And that's about equal to 9.82. Um, it really depends on why it's not 9.81. It really depends on which approximation of Earth's mass and radius are, and like it's not what approximation, but how many decimal digits they're going out to. But another thing we should know is, hey, the Earth, we said it's a sphere, right? well, and these equations still work even if it's slightly non-spherical. Like it turns out that our Earth is more of an oblate sort of shape rather than being a perfect sphere. So it actually turns out that you know, gravity can be slightly different in some directions, but it's really, the approximation for gravity, that change by it not being a sphere would be somewhere like a change out here. And for our purposes, we don't really need to know that as exact. And now I will talk about these derivations here. How did we do this? We already discussed this, that I is a function of x, j, and k are both functions of x and y. Now we have a few terms to get through. We have di dk, sorry, di dx, partial I partial x, partial j partial x, partial j partial y, partial k partial x, and partial k partial y. So, okay, we have partial I partial x is equal to limit as delta x goes to 0 of the magnitude of delta I over delta x in the negative r hat direction. And if we draw this diagram, we can see that using the similarity of triangles rule from geometry, we have that, I goes this way, I plus delta I goes this way, delta I goes this way in the negative r direction. And so we have delta I over the magnitude of delta I over the magnitude of I, where the magnitude of I is just 1. So that's this over this. That's similar to this is dx, this is di, this is I, this is a cosine p. There's a geometric way to show this, which I won't go over. And doing that, we can move dx to the bottom, or actually we don't need to do that. We can have this is equal to this. We plug this into here, the dx's cancel out, and we'll get its 1 over a cosine phi. This is negative because the negative goes here, r hat goes here, and then we do this multiplication here like we did earlier, and we'll get this term right here. Then for d, and that was d dx, partial I partial x. Partial d partial x, we write the similar form. We know that it goes in the positive I direction. This delta j goes in the positive I direction. So we have magnitude of delta j over magnitude of j, which is 1, is equal to delta x over the length here or here, which is a tangent phi, which you can also show geometrically, which I won't do here. And now we plug this into here. We have negative I, and then this, is over a over tangent phi. So it's tangent phi over a, and the delta x's go away. We're left with this term. Then for dj dy, we write it in this form. We know that it's in the negative k direction, k hat direction, and we know delta j over j is proportional or equal to a delta phi, where phi is latitude, divided by a. So that's this. The a's cancel out, we get this. And we also know that we're looking for delta y. Delta y is equal to a delta phi, because this is delta y, and it's equal to the side length divided by the angle, by the angle formula, or angle arc length formula. So we get delta j is equal to delta y over a, the magnitude of delta j. And that goes into here, and we're left with negative 1 over a k hat. And now just for clarification, this thing right here is j. So the magnitude, which has a magnitude 1. This right here is also j. and we showed it here that this is off. It was just the similarity of triangles, and in this case, we also use this arc length formula. So this is, I'll just write it here, arc length. And each of these were just a similarity of triangles. Okay. And finally, we're looking at delta partial k partial y. We write it in a similar form, and we know that it's pointing in the negative j hat direction. We can write in this case, here's k, and then k1 is k2 is here. And I sort of wrote that a little bit weird, but this I wrote a little bit off. It looks like this is going in this direction, but it's really going in this direction. So I should really fix these. It's such a small triangle we can't even see, but this is a triangle. This is delta k, and it's it's pointing in the z direction. Let's see here, pointing in the z direction. Okay. So we can use similarity of triangles, dk over k, the magnitude of dk, so magnitude over magnitude, because a magnitude is a length. These are just vectors; they point in a direction. They have a magnitude. We know, so that's why we're doing these magnitudes. So it's delta k over k. The k goes to 1, and that's similar to this delta y over a. And plugging this in here, we get negative 1 over a j hat. And it's very difficult to draw the delta k delta x term, but you have to think, it's going out, like out of the page in the outward direction. But you can write the two triangles that we're looking at. This is written in a similar form. That's delta x. These are supposed to be delta k. That's k over k. This goes to 1. And this delta k, magnitude of delta k divided by magnitude of k goes to 1 is equal to dz over a. And plug this into here, and we'll get 1 over a I hat. So that shows geometrically how we're thinking about this very, very important aspect of the derivation, the main part here. So you have to be able to visualize what the Earth looks like and segment out different directions based on each, and then use the similarity of triangles, and in some cases the arc length formula, and you will come out with these solution. And you'll get a very amazing equation like this. And so in the next video, I will be doing the next two videos, I will be doing the completing this equation set. What we're missing now is the mass continuity equation and the moisture continuity equation, which will go in the thermodynamics section right after I release the mass continuity equation video. And I'll talk in those videos about what will be happening next. So if you like the channel, like and subscribe, and stay tuned for more videos in the future.